Good afternoon, ladies and gentlemen. My name is Tomislav Dragicevic. I'm professor here at DTU, and I'm the chairman for today's PhD defense of Mr. Andreas Horst Venzke. And in the following minutes, I will introduce the examiners for the thesis, the PhD candidates themselves, and the supervisors. And I will also wish a warm welcome to everybody present in the room and on the web. So we have three examiners today. First one is Associate Professor Duncan Calloway from the University of California, Berkeley. Second one, also external, is Andy Soon, an Associate Professor in the School of Industrial and System Engineering at Georgia Institute of Technology. Then we have one external examiner, which is Associate Professor Jalal Kazempur. The PhD candidate, as mentioned, is Mr. Andreas Venzke, and his main supervisor is Associate Professor Spyros Chaziavaliidis. I don't know if I pronounced it correctly, and his co-supervisor is Professor Pierre Pinson. So now I will inform you how we will proceed with the defense. So after stating the title of the lecture, which is Machine Learning and Convex Optimization for Secure Power System Operation, then the candidate comes from Department of Electrical Engineering here at DTU. And afterwards, he will give a 45 minutes presentation, after which the external and internal examiners are entitled to give him questions. Moreover, everybody present also at the defense is also entitled to ask questions, but in coordination with me as a chairman. But I will ask after all the questions are done if there are any additional questions. So after the lecture, we will start with the questioning, and without further ado, I would leave the floor to Mr. Venzke. So please go ahead.
Thank you so much, and very warm welcome to both those attending here physically, as well as to the ones attending virtually. So the title of my PhD thesis is Machine Learning and Convex Optimization for Secure Power System Operation. And I would like to start with the motivation. So in order to reduce CO2 emissions, we see a worldwide increase in the share of renewable energy in the electricity mix, such as wind and solar generation. And this renewable energy leads to the phasing out of conventional fossil fuel power plants. And traditionally, these central fossil fuel power plants, such as coal and gas-fired power plants, were highly predictable, and they also provided controllability to the power system operator. Now, with the increase in renewable generation, the uncertainty levels in the power system increase significantly, posing challenge to the system operation. At the same time, there is less controllability available to the system operator to ensure the security of the power system. And we also see that there is a strong public resistance against the upgrades of the electric transmission system, such as the building of new overhead lines. And overall, these trends lead to the electric power system being operated closer to its limits. And one of these examples we can see on the right figure, where we see the redispatch volume in the German transmission grid over the last years. And redispatch refers to the power system operator taking a corrective action to ensure the security of the power system. And we can see that this redispatch volume has significantly increased, primarily due to the increase in renewable generation in the German electricity mix. And also the costs associated with these redispatch actions have increased more than 25-fold from the year 2010 to the year 2018, with the cost increasing from 13 million euros to 355 million euros. So the first research direction of my PhD thesis is to develop optimization methods that ensure the security of the power system while explicitly accounting for the uncertainty in renewable generation and being able to fully utilize the available controllability from, for example, large offshore wind farms. As an alternative to optimization methods, we can also use machine learning for power system operation. And on the left-hand side, we can see the number of publications over the last 20 years that have proposed machine learning approaches for power system operations. And we can see that in the last 5 years, the number of publications has significantly increased. And this renewed interest can be attributed to the successes made in the field of deep learning in application areas such as image recognition, natural language processing, and gameplay. And these machine learning methods in power systems can achieve computational speed-ups of more than a factor 100 compared to conventional methods. So for the example of system security assessment, that is screening a large number of operating points for potential failure risks, neural networks can achieve a speed-up of more than a factor of 100 compared to conventional methods. And similar computational speed-ups can be achieved with using neural networks to learn solutions to so-called OPF or optimal power flow problems, which are important tools for power system operation. However, these promises reported in the research literature have not yet found application in practice. And that is because system operators do not trust these black box tools. And in case they have some internal errors, this could jeopardize the system security. So the second research direction of my thesis is to build this missing trust by removing barriers for machine learning in safety critical power system operations. And now turning back to the first research direction, the optimization methods for secure power system operation under uncertainty, I want to introduce the AC optimal power flow problem. This is an essential tool for secure power system operation, and it is an optimization problem that minimizes in its objective function, for example, the total generation cost, subject to a range of constraints. And these constraints include the AC power flow equations and operational constraints, such as the loading of transmission lines. The AC-OPF problem is a non-convex and NP-hard problem. And on the right-hand side, we see an illustrative feasible space, meaning the set of all solutions that satisfy the constraints to the non-convex AC-OPF. And we can see that that feasible set is highly irregular. And in practice, this has two implications. The non-convexity has two implications. The first one is that if we use a non-convex solver, we do not have a guarantee that we identify a feasible solution, even if it exists. And the second one is that if we obtain an optimal solution, it is only locally optimal, and we cannot specify the distance to a globally optimal solution. And that is why there has been significant research effort in the last decade into convex relaxations of the AC-OPF problem to address the non-convexity. And these include the semidefinite, second-order cone, and quadratic convex relaxations. And in order to understand the concept of convex relaxations a bit better, I included the illustration on the right that in red shows the non-convex set of an AC-OPF problem. The system cost decreases going downward. So we have two optimal solutions. On the left, the globally optimal solution, and on the right, a locally optimal solution. Now, if we have an exact convex relaxation of this non-convex AC-OPF problem, then the optimal solution to the convex relaxation, shown in blue, corresponds to the globally optimal solution to the non-convex problem. And this exactness is required for the solution to be AC feasible, that is to satisfy the constraints of the original non-convex problem. If we have an inexact convex relaxation, shown in orange, then the optimal solution to the inexact convex relaxation corresponds to a non-physical solution that violates the constraints, as the solution is not part of the original non-convex space. So the first objective of my thesis is to develop tractable and convex AC-OPF formulations which consider uncertainty from renewable generation while ensuring the AC feasibility of the solutions that we obtain to the convex relaxations. And the contributions of my thesis with respect to this objective are the following. We introduced the first convex formulation of a chance-constrained AC-OPF with near global optimality guarantees. So chance constraints means here that constraints with uncertain variables are satisfied with a maximum allowable probability of violation. We achieved two tractable formulations for a Gaussian and a robust uncertainty set, And we introduce systematic penalization methods to ensure the AC feasibility of the solutions. And we extend this framework to both power system security criteria and interconnected AC and HVDC grids. Now turning back to the second research direction, removing barriers for machine learning in power systems, the first barrier we address is the lack of high-quality datasets. So the performance of any machine learning tool highly depends on the quality of the dataset used, and historical data of measurements only contains limited information of abnormal or insecure operating conditions. And that is because, fortunately, the power system is operated in a secure state most of the time. And if we want to train now, for example, a machine learning classifier to detect operating points that can lead to insecure operating conditions, then we need to create data sets to train these tools. And when it comes to the dataset creation, we face two challenges. The first one is the high problem dimensionality. So we have to consider a large number of variables. And the second one is the class imbalance. So meaning a large portion of the possible operating region corresponds to insecure operating regions. So on the figure in the left, we show the possible operating space as the black square, and inside in gray, we have the secure space. Now, if we use a brute force sampling algorithm that does basically a grid search over the entire possible operating space, we obtain a data set of low quality. It is imbalanced and it doesn't characterize the secure space in detail. What you would like to obtain is a data set shown on the right. So a data set that is balanced between secure and insecure operating points and that characterizes the security boundary in detail. Regarding the second barrier that we want to remove, the black box nature of neural networks, it is important to note that the performance of neural networks is only evaluated empirically on the unseen test data set in power system applications. And it has been shown in the machine learning community that for image classifiers, so-called adversarial examples exist. So those are small perturbations to the input of a neural network that lead to a misclassification of the output. So what we see on the figure below on the left is an image of a panda that gets correctly classified as a panda by a state-of-the-art image classifier. If we now add some very small, carefully crafted noise to this picture, the resulting image is misclassified as a gibbon, where to the human eye, both images look exactly the same. And these neural network misclassifications are poorly understood, and these adversarial examples also exist for safety-critical power system applications, posing a major obstacle towards their adoption in practice. So the second objective of my thesis is to remove these barriers for machine learning in safety-critical power system applications. And regarding the first barrier, the lack of high-quality data sets, we propose modular and parallelizable methods to efficiently create balanced data sets with a detailed description of the security boundary. And one of the key steps of these algorithms are infeasibility certificates based on convex relaxations, which allow us to a priori classify large parts of the input regions as insecure. Related to the second barrier, the black box nature of neural networks, we introduced the first rigorous framework to obtain formal guarantees of neural network behavior. And for security classifiers, that is neural networks trained to predict system security assessment, we obtain the largest input regions to these neural networks for which we can guarantee a certain classification, and we're able to identify adversarial examples. And then using those identified adversarial examples and retraining the neural network classifiers, we can improve their robustness. For the case of learning solutions to OPF problems with neural networks, we're able to provide worst case performance guarantees. And now coming to the outline of the remainder of my presentation. First, I'd like to provide some more details on the convex optimization methods for secure power system operation under uncertainty. And then I would like to focus on removing barriers from machine learning. In particular, I will present efficient methods to create data sets and introduce a framework to obtain formal guarantees of neural network behavior. Then I'll conclude and provide some future directions for research. And overall, this thesis summarizes 8 scientific publications, 6 journal publications, and 2 conference articles. So now I would like to talk a bit more about convex optimization methods for secure power system operation under uncertainty. And in the thesis, there are 4 publications included related to this topic, and I'll focus on the second one as it introduces the framework. So our motivation is that we would like to account for the uncertainty in renewable generation in the AC-OPF problem. And existing work can be roughly divided along 3 directions. The first one relies on the DC-OPF approximation, which is a linear approximation of the AC-OPF problem that neglects active power losses, reactive power, and voltage magnitudes. And in practice, this can lead to substantial errors and constraint violations. The second research direction uses an iterative approximation of the non-convex AC-OPF. However, we do not have any guarantees related to this iterative procedure. And then the third direction utilizes convex relaxations. And here, as we've seen in the introduction, it is of high importance to obtain solutions to the convex relaxations that are in fact AC feasible. So our work proposes the first semi-definite formulation of a chance-constrained AC-OPF that can obtain AC feasible solutions with near global optimality guarantees. And I would like to start with the description of the semi-definite relaxation of the AC-OPF. We follow the work of Javad Lavai and Stephen Lowe and transform the voltage variables to a system matrix of voltage products. So W can be written as X transposed, with X being equal to the real and the imaginary part of the complex bus voltages. And then a simplified version of the AC-OPF problem is shown below, where in the objective function, we minimize the generation cost, subject to a range of constraints, including the active and reactive power balance, upper and lower limits on bus voltages, active branch flows, and apparent branch flows. And then we also have the decomposition constraint, so that W should be able to be decomposed into X transposed. And now this decomposition constraint can be equivalently reformulated as W being positive semi-definite and the rank of W being equal to 1. And now with this reformulation, we achieve that all the non-convexity of the AC-OPF formulation is encapsulated in the last rank constraint. So if we remove that rank constraint, then we relax the non-convex AC-OPF to a convex semi-definite program. And now if we solve that semi-definite program and the W that we obtain does in fact have rank 1, then the semi-definite relaxation is exact and we have obtained the globally optimal solution to the non-convex AC-OPF. However, if the rank of W obtained is higher than 1, then the semi-definite relaxation is inexact and the solution we obtain is non-physical and will violate some of the constraints of the original problem. And now we include chance constraints in the semi-definite relaxation of the AC-OPF. And for that, we model as stochastic variables the wind infeeds as the sum of a forecasted wind generation value plus a forecast error. And in the formulation, we now include a joint chance constraint. So that means that all the physical constraints should be jointly satisfied with a defined probability 1 minus epsilon. And as a result of the introduction of the stochastic variables, the system state is now a function of the forecast errors. So depending on the forecast error realizations, the system state changes. And now the resulting convex chance constraint AC-OPF formulation is infinite dimensional. So due to the uncertain variables, there is an infinite number of constraints, and this problem is generally considered to be intractable. So now we have to answer 2 questions in order to achieve tractability of this problem. The first one is, how do we model the forecast error distributions? And there we propose 2 approaches. The first one uses scenario-based methods and robust optimization, and we refer to that as robust uncertainty set in the following. The second one assumes Gaussian distribution of the forecast errors, and we refer to that as Gaussian uncertainty set. And then the second question we have to answer is, how do we approximate W as a function of the forecast errors? And here we rely on a piecewise affine approximation that I will explain in more detail in the following. So for the robust uncertainty set, we do not make any assumptions on the underlying distribution of the forecast errors. And then we have a result from literature that says we should at least draw a certain numbers of scenarios to enclose 1 minus epsilon of the uncertainty set with a confidence beta. And what we can see below is for two uncertain variables, the resulting uncertainty set, where the rectangular uncertainty set encloses all these drawn samples, and W0 refers to the forecasted system state. And now we need to describe how the system changes. So the system state changes as a function of different forecast error realizations. And we do that by introducing a piecewise affine approximation that interpolates from the forecasted system state W0 to the vertices of the robust uncertainty set. And then the chance constraints with this approximation are convex, and using a result from robust optimization, it is sufficient to enforce the joint chance constraint at the vertices of the rectangular uncertainty set. So with that, we obtain the first tractable formulation. And now related to the Gaussian uncertainty set, we assume a Gaussian distribution of the forecast errors. So the resulting uncertainty set is an ellipsoid. And then we also approximate the joint with individual chance constraints with the same maximum allowable probability of violation. And again, in order to describe the system state as a function of the forecast errors, we introduce a piecewise affine approximation from the forecasted system state to the endpoint of the ellipsoid axis. And this allows us to analytically reformulate the scalar chance constraints and approximate the semi-definite chance constraints by enforcing them for the vertices of the dotted rectangular shape shown below. And now for both tractable formulation for the robust uncertainty set as well as for the Gaussian uncertainty set, we want to identify rank 1 solutions, W solution matrices. And for this purpose, we introduce a systematic iterative penalty term on active power losses. So we augment the objective function, which minimizes the generation cost, with an additional penalization term and a penalty weight mu. And then at the beginning of the procedure, we start with a penalty weight that evaluates to 0, and then we successively adjust the penalty term to identify rank 1 solution matrices. And I show some results on this procedure for a 53-bus test case with 3 wind farms and a robust uncertainty set. So we consider 9 W matrices. And as a heuristic measure to determine whether the obtained W matrices have rank 1, we compute the eigenvalue ratio of the first to the second eigenvalue of W, and that has to be larger than 10 to the power of 5. And what we see below in the upper figure is the eigenvalue ratio versus the number of iterations of the procedure. And below, we see the maximum constraint violation as a function of the number of iterations. And what we can note is that at iteration 1, when the penalization weight is 0, so the penalty term evaluates to 0, then we do not obtain all rank 1 solution matrices. So when applying the outcome to the forecasted system state and the vertices of the uncertainty set, we observe significant constraint violations. And then as we iterate, more and more of the W matrices admit a rank 1 solution. And at iteration 20, all W matrices are rank 1. And we can see that the maximum constraint violations evaluate to 0. So we have identified AC feasible solutions. And now I would like to summarize some of the key results from publication B, where we compare both the approach based on the robust and the Gaussian uncertainty set to 2 relevant approaches from literature. So first, a robust DC-OPF formulation, and second, an iterative non-convex chance-constrained AC-OPF, assuming Gaussian uncertainty set. And now using realistic wind forecast data for an IEEE 118 bus system with maximum chance-constraint violation probability of 5%, we find the following. First, the DC-OPF approximation leads to substantial constraint violations as it neglects part of the relevant variables. Our approach based on the robust uncertainty set achieves compliance with the chance constraint, and both our approach and the approach from literature based on the Gaussian uncertainty set can lead to violation for some of the time steps, as the wind forecast data is not purely Gaussian distributed. And overall, our approaches achieve a near global optimality guarantee of more than 99%, So that means we can upper bound the distance to the global optimum to at most 1%. So that concludes the part where I dive a bit deeper into the convex optimization methods for secure power system operation under uncertainty. And now I want to focus on the part where we remove barriers for machine learning in power systems. And first, I want to talk about efficient methods to create data sets. And here, 2 publications are included in the thesis, and I'll focus on the second one. So as a reminder, the barrier we would like to tackle is the lack of high quality data sets. So that means we need to create those data sets. And existing work related to data set creation relies mainly on 2 directions. The first one uses importance sampling. So that is having multiple rounds of sampling where the sampling is biased towards regions of interest. And as we've seen in the beginning, the possible operating region in terms of classification is largely unbalanced. So large parts of the possible operating region corresponds to insecure operating points. And therefore, this procedure can fail at recovering the secure space, but it can also miss relevant parts of the secure space. And then the second approach relies on composite approaches and bind copulas that are used to enrich historical data. And this approach, of course, highly depends on the quality of the historical data available. So the approach that we put forward is modular, so it can also utilize both importance sampling and composite approaches. It is parallelizable, and it does not rely on historical data, but it can leverage historical data. And as a key ingredient, we use infeasibility certificates based on convex relaxations to a priori classify large parts of the input region as insecure. And now I want to explain these infeasibility certificates in a bit more detail. So here we see again the input space, and in green shown the secure space. And the secure space is defined by the operating points complying with both dynamic and static security criteria. And the goal is for a defined input space capital D of dimension lowercase d to obtain a balanced data set characterizing the boundary of the secure space. And for example, for an operating point that is characterized by both the generation dispatch and the voltage set points of the generators, the possible operating space simply corresponds to the minimum and maximum technical limits on these variables. And now the prerequisite for the assessment of computationally intensive dynamic stability criteria is the feasibility to static security criteria. And these can be described in the AC-OPF problem. And that means that the AC feasible space, shown here in black, encapsulates the secure space. And now we can use convex relaxations of the AC-OPF, shown here in gray, which encapsulate the AC feasible space, as infeasibility certificates. Meaning we can take an infeasible operating point, x hat, and compute the closest dispatch x star that is feasible to the convex relaxation of the AC-OPF. And then Dan Molzahn has proposed to use hyperspheres with a radius r star as infeasibility certificates. So that means that any operating point that is within the hypersphere is guaranteed not to be part of the feasible space of the convex relaxation, and as a result, also not part of the secure space. And what we propose to use instead is separating hyperplanes as infeasibility certificates. So all the operating points on the left-hand side of the hyperplane are guaranteed to be not part of the convex relaxation's feasible space and also not be part of the secure space. And now what we observe is if we draw multiple samples and identify hyperplanes, we form a convex polyhedron. And we have efficient methods available to sample from within a convex polyhedron. And we propose an algorithm that allows us to a priori minimize this unclassified remaining input space. And this works basically like this. So we first start with the input space. We draw a sample. If it's infeasible, we identify the closest feasible sample to the convex relaxation, obtain a hyperplane. Then we draw another sample now from the updated description of the convex polyhedron. And by doing that, we successively decrease the unclassified input space. And I show a comparison of the infeasibility certificates based on the hyperspheres and the hyperplanes in the above figure as a number of iterations of this algorithm. And at iteration 0, the reference normalized volume of the possible operating space is 1. And we can see that the hyperplanes are very efficient at reducing the unclassified volume compared to the hyperspheres, and also within fewer iterations. And just to put the number into perspective, so a volume reduction from 1 to 10 to the minus 5 implies that in expectation, we have to draw at least 100,000 samples randomly from the initial unclassified input space to identify one potential feasible sample. So that means that the infeasibility certificates allow us to discard vast parts of the input space as insecure. And if we were to sample directly from the possible operating region, it would be very hard at identifying secure samples. And now we use these infeasibility certificates in an efficient algorithm to create data sets. So first, we run this algorithm to minimize the initial unclassified input volume and obtain this description of the convex polyhedron. And then we draw and classify a large number of samples from within the convex polyhedron. And for those samples that correspond to insecure operating points, we identify the closest secure operating points to obtain a detailed boundary identification. So in publication F, we focus on static security and solve an AC-OPF that minimizes the distance to the closest feasible point to the AC-OPF. And in publication E, we focus on dynamic security and propose to use directed walks and sensitivity measures. So we traverse the possible operating space towards the boundary and then move along the boundary to characterize it in more detail. And then we fit a multivariate Gaussian distribution to the obtained secure samples and, if available, historical data of secure operating points. And then we draw and classify a large number of samples from this fitted distribution. And this serves both to characterize the inside of the secure space, but also the boundary in more detail. And here I show some of the key results from publication F, where we create data sets for 15 PGLib-OPF test networks, up to 500 buses, and a dimensionality of 125. The security criteria we consider is both the feasibility to the AC-OPF and the N-1 security constrained AC-OPF. And what we show for these 15 test cases is that the infeasibility certificates allow us to drastically reduce the initial unclassified input space with a medium reduction value of 10 to the minus 8 and up to 10 to the minus 40. And we also see that if we then directly sample from the resulting convex polyhedrons, we're able to identify secure samples. So it means that the convex polyhedron is a somewhat tight enclosure of the secure space. And for the 15 test networks, we create balanced data sets with an average of 46.5% of secure samples. So we're close to the desired 50%. So with that, I would like to wrap up the part where I talk about efficient methods to create data sets. And now I want to move on to the framework to obtain formal guarantees of neural network behavior. And here I consider 2 publications, and I will talk about both of them. So as a reminder, what we would like to address is the barrier that neural networks currently are used in power systems as black box tools. And for that, we introduced the first framework to obtain provable guarantees of neural network behavior for both classification and regression tasks. And in publication G, we focus on classification and use as a guiding example security assessment. So meaning if we have an operating point that is characterized, for example, by the generator set points in terms of active power and voltage, we use a neural network to predict whether these operating points are secure or insecure. And then for publication H, we focus on a regression task. And the guiding example we use here is using neural networks to predict solutions to DC-OPF problems. And we can understand the DC-OPF problem as a mapping from a power system demand, PD, to an optimal power system generator dispatch, PG. And this optimal dispatch PG is the solution to the DC-OPF problem, which, given a system demand PD, minimizes the generation cost subject to the nodal power balance and generation and transmission line constraints. And now the neural network architecture that we consider is a feed-forward architecture where we have an input layer, subsequent hidden layers, and an output layer. And at the input layer, we apply a weight matrix W1 and a bias vector B1 to the input X to the neural network. And then at each of the neurons of each of the hidden layers, we apply a non-linear ReLU activation function. So that is, we take the maximum between the input to the neural network, denoted with Z hat, and 0, and propagate that to the output Z of the neuron. And then between each of the hidden layers, we again apply weight and bias matrices, and then we finally obtain the output prediction of the neural network, denoted with Y. Now, the standard procedure for neural network training is to split the data set at hand into a training and a test data set. And then during training, we minimize a loss function. For example, the root mean squared error for regression tasks or the cross entropy function for classification tasks. And during this training procedure, we use the training data set and we update the weights and biases of the neural network using stochastic gradient descent to minimize the loss function. And then after training, the weights and biases are fixed, and we test the neural network performance by evaluating the neural network on the unseen test dataset samples. And what recent literature has shown that for both classification and regression tasks in power systems, we achieve low errors on the test set and a computational speed up of more than a factor of 100 compared to conventional methods. But the major obstacle remains, and that is that we do not have any guarantees on the neural network performance. So the goal, in order to obtain provable guarantees of neural network behavior, we want to include the trained neural network equations in an optimization framework. And for that, we in particularly look at the non-linear ReLU activations, and we reformulate those using we reformulate the max operator of the nonlinear ReLU activation functions using binary variables. So on the right-hand side, we can see in blue the ReLU function. So if the input to the neural network Z hat is below 0, then the output is 0. If it's above 0, then the neuron propagates the input Z hat to the output Z. And then basically, if I have a binary variable, we see that we can have one part where the neuron output is 0, where also the binary variable evaluates to 0. And conversely, if the output of the neural network is the output of the neuron is equal to the input to the neuron, then the binary variable evaluates to 1. And overall, this allows us to obtain a mixed integer linear reformulation of the trained neural network equations. And now in publication G, we use this reformulation to obtain formal guarantees for security classifiers. And for this, we formulate mixed integer linear programs. And here we consider 2 guarantees that I will explain a bit more in detail in the following. So if we have a given reference operating point, xref, with a certain classification y1, meaning the output y1 is larger than y2, that could correspond, for example, to a secure operating point, then we can calculate whether a potential adversarial example exists within distance epsilon of this reference operating point. And for that, we maximize y2 minus y1, subject to the mixed integer linear reformulation of the trained neural network and the infinity norm as a distance metric that constrains x to be within distance epsilon of x reference. And now if we solve this optimization problem and the objective value is that we obtain is negative, meaning that y2 minus y1 is smaller than 0, then we have obtained the provable guarantee that within distance epsilon, no adversarial example exists and no input exists that can change the classification. Conversely, if the solution to this optimization problem is the objective value is positive, then we have identified a potential adversarial example and we need to analyze it in more detail to determine if it is in fact an adversarial example. And then the second type of guarantees that we can extract are the largest input regions around the reference sample with the same classification. And for that, we minimize the distance epsilon to an input to the neural network that leads, in fact, to a change in classification. And here again, if we solve this mixed integer linear program, then we obtain the provable guarantee that no input exists that is closer than epsilon to the reference operating point that leads to a change in classification. And now I visualize these regions with a guaranteed mapping for a security classifier from publication G. So what you can see here on the X and Y axis are two inputs to the neural network, two generator set points. And then I've done a detailed resampling to show the neural network predictions. So in green, we see the samples that are classified correctly as secure. In red, the ones that are misclassified. So those are at the boundary, at the classification boundary. And then in blue, the correctly insecure classified ones. And now with the black axis, we see the reference samples and around the regions with the guaranteed mapping. And now this framework to obtain formal guarantees has two key advantages. So the first one is that for the first time, we obtain guarantees for continuous input regions that map to a certain classification. So before, we could never be sure whether between samples there doesn't exist an input that changes the classification, but here we have the provable guarantee for the boxes that doesn't exist any input. And then the second benefit is that by computing the largest regions of guaranteed classification, we're able to unveil the mapping of the neural network. And this makes the neural network interpretable to system operators. And now turning to the regression task for which we obtain formal guarantees, we focus on learning solutions to DC-OPF problems with neural networks. So here I show the DC-OPF mapping. So we have the power system demand that lives within a defined domain D. And then we map that to an optimal generator dispatch PG. And because this optimal generation dispatch is the optimal solution to the DC-OPF problem, it satisfies both the generator and the transmission line limits. And now, if we use a neural network to approximate this mapping by predicting P hat G, we see that we do have some approximation errors. And these also can translate into violation of the physical constraints of the system, namely the generator and the transmission line limits. So what we propose in publication H is to use mixed integer linear programming to obtain worst case guarantees over the entire continuous input domain to the neural network that we define. And now we can determine first the maximum generator and line constraint violations. So for any input that lives within the defined input domain, what is the maximum generator and line constraint violation based on a wrong neural network prediction? And then secondly, what is the maximum distance between the neural network prediction and the optimal generation variables that are the solution to the DC-OPF problem? And now I would like to summarize some of the key results from publication H. So here we consider a range of PG-lib-OPF networks up to 300 buses. And we have a data set of 100,000 samples with the power system demand mapped to the optimal solution to the DC-OPF within 60% to 100% of the system loading. Then we use 80,000 of those samples to train neural networks and 20,000 for testing. And what we find is that the average test set performance of the neural networks are satisfactory. So they have a mean absolute error of less than 1%, which would be considered as a highly accurate neural network. However, if we solve the mixed integer linear programs to obtain the worst case guarantees on the neural networks, we observe that the worst case violations are substantial and up to 24% of the maximum system loading. So if for the worst case input, we were to apply the neural network prediction to the physical system, this would lead to a substantial overloading of some of the equipment. And then also the worst case guarantees that we obtain, both on the distances and the violations, are 1 order of magnitude larger than the empirical worst case over the entire data set. So if we just take the maximum over the 100,000 data sets, then the worst case guarantees are roughly 10 times larger. And now I would like to go to the conclusions and formulate some future directions for research. So in this presentation, I've proposed convex AC-OPF formulations, which consider uncertainty from renewable generation. And I've shown that we can achieve tractability for a Gaussian and a robust uncertainty set. And we introduced a systematic penalization procedure that allows us to obtain AC feasible solutions with near global optimality guarantees. And then we also looked at removing barriers for machine learning and power systems. And to this end, we introduced the first framework to obtain provable formal guarantees of neural networks for both classification and regression tasks. And we proposed efficient methods to create high-quality data sets. And these methods have the potential to build the missing trust of operators in these tools. And now in terms of future directions for research regarding the convex optimization methods, it would be of interest to look at distributionally robust optimization as an alternative to model the Gaussian and modeling the uncertainty using the Gaussian and the robust uncertainty set. And then as a second research direction, it would also be of interest to investigate the use of iterative penalization methods within this framework, which can guarantee to recover AC feasible solutions. And related to the removing of barriers for machine learning in power systems, I foresee as a next step to combine both the dataset creation and the formal guarantees in a comprehensive framework to develop reliable machine learning tools. And this would entail first the creation of datasets, leveraging if available historical data, then training of neural networks and the evaluation of their performance, including the evaluation of formal guarantees that we can obtain on their behavior. And then if the performance, including the formal guarantees, is not satisfactory, so for example, the worst case performance of the neural network does not meet the system operator specifications, we return to the first step and, for example, enrich the data set with identified adversarial example. And we repeat this procedure until we obtain a reliable machine learning tool that has certified performance guarantees and can be used as a tool in practical safety-critical power system applications. With that, I would like to thank you for listening.
Thank you very much, Andreas. And I suggest now we take a 5-minute break to refresh, and we come here, let's say, 1:55 and start with examination. Yeah.